recording and sharing the screen. Want to give you a heads up because I have a few things that I need to do family-wise right after class. Notes will probably not be uploaded until towards the end of the day today. I'm sorry if that's a problem for anybody. I'm guessing it might be more of a problem for folks who are not here, but that's not going to probably happen until early this evening. Today is the 30th. We're going to start looking at that next section that deals with functions and graphing and linear things and systems of equations. Olivia, I got you. Thank you. Exam 2 on all of the solving equations that we just finished, which includes solving first degree equations, solving quadratic equations, solving absolute value equations, radical equations, equations with fractional exponents, solving inequalities. And in our search of solving equations and inequalities, we also had to learn about complex numbers because some equations are only solvable with complex numbers, and interval notation is a shorthand way of writing our solutions for inequalities. That's what all of the homework through the problem set is on, and that's what the test is on. Does anybody have any questions on any of the homework or the problem set?
You said we get a credit for showing corrections or your check your work?
It's showing your checks, yes. I'm giving extra credit for checks. Also, did everybody make note of the fact that this test is due Saturday, not Sunday, Saturday. I am hoping that if everybody submits their tests by Saturday and their work by Saturday, I can grade them Sunday, and so that you'll know on Monday how you did. Remember that I'm not going to grade it if you don't give me your work in Blackboard. For Blackboard to work, you have to be using Chrome or Firefox, or if you've got an iProduct, you have to use an app. If anything goes wrong when you try to submit it, then you can email it to me. But again, it's better if you submit your work in Blackboard than if you send it to me as an email. You submit your work in Blackboard through Blackboard. I can annotate it, I can grade it, I can do the red pen thing, and I can quote unquote give you your paper back. You can look at your marked up paper in Blackboard. The ones that some people have sent me emails, depending on the format in which it goes in, there are some emails that no matter how hard I try, I can't write on the paper. And so I can't return the quote unquote return the graded paper. So again, try Blackboard first, but if it doesn't work or what I'm grading, if I can't see it in Blackboard, I'll send you an email and ask you to send me your work that way. So please hold on to your work. Do not throw it out. Also, my office hour at 9 o'clock in the morning on Monday is canceled. I will reschedule it and have an office hour at 2 o'clock in the afternoon on Monday. I hate having to do that, but I got a dentist appointment at 8 o'clock and I should be definitely back by my first class at 10, but I'm not positive that they'll be done by 9. I hope they're done by 9. I hope there's nothing wrong, but you never know. You know how that is. So, okay, if all of that is all right and there are no questions, let's start looking at functions. And talking to my 11 o'clock section after class, most people said that this was review for them. This was something that they had seen previously. But again, I know everybody comes from a different place, and so I'm going to treat this as new content. So hopefully I'm not going too slow for folks who are real familiar with it, and hopefully I'm not going too fast for people who are unfamiliar with it. So one way or another, please let me know. Before we look at functions, we've got some definitions. And the first definition that I want to give is that of a relation. And we're going to define a relation as a set of ordered pairs. when I talk about ordered pairs, most people think of things like ordered pairs XY. Sometimes that X value you see called an abscissa. Sometimes that Y value you see called an ordinate. We're going to mostly focus on numeric ordered pairs, but you see examples of relations that aren't numeric. One example would be when I get a class roster at the beginning of the semester. When I get a class roster, I get a set, and in that set, I get all of the students' names, and so they're usually last name, comma, first name. And so that roster would be in a relation where we're pairing people's last names with their first names. I'm leaving a space in between these for a reason. I'm going to go back and fill in the space in a couple minutes. Another example, it would be numeric, but not necessarily what you would think of in a math class. Sometimes when you go to a doctor's office, when you check in, they get information from you, and they look at a combination like your height and your weight. And so if I had all of this doctor's patients, that would be a set of ordered pairs. But again, in this class, we're going to focus more on relations. And sometimes sets are given names, uppercase letters. I could have a set of ordered pairs. I could have the pairs 1, 1, 2, 4, 3, 9, -1, 1, -2, 4. And that would also be a set of ordered pairs. When I look at a relation, when I look at a set of ordered pairs, there's a couple of other things we need to be able to get from them. One is the domain. And the domain is also a set. It's the set of the first members of the ordered pairs. And so some people think of them as the X values. And if the domain is the fancy name that's given to the first members, the X values, we have another term, the range. And the range is the set of the second members of the ordered pairs. And some people think of those as the Y values. And when I think of ordered pairs being X, Y, I think back to when I first started learning how to do things like graph. And I would look at that pair of numbers and I'd be like, I don't know what my problem was. I would look at them and say, okay, all right, which is the X value, which is the Y value? And somebody told me, silly, they're in alphabetical order. X comes before Y. The first one's the X and the second one's the Y. And that line of reasoning helped me remember the abscissa is the X value, the ordinate is the Y value or the second, because I'm looking at the idea of putting them in alphabetical order. A comes before O. Likewise, when I look at those sets, if I put them in alphabetical order, domain comes before range. And so that idea of putting them in alphabetical order helps me personally remember that the domain is the first one, the X value is the range is the second one, the Y values. And that idea of going through and putting them in alphabetical order, those of you who are following this class with the advanced algebra and trig class, you're going to see a relationship between coordinates and your trig functions. And that idea of putting them in alphabetical order can help you remember which is which. Ryan, remind me at the end of class and I'll add you in. And somebody else I also just let in. If you come late, please stick around to the end of class and remind me to add you to the attendance. But domain is the member or set of the first members, range is the set of the second members. Domain is sometimes abbreviated with an uppercase D. Range is sometimes abbreviated with an uppercase R. And so going back to these examples, the first one, if I ask you what the domain is, when I look at the names on the roster, wouldn't the domain be the set of last names? And wouldn't the range in my ordered pairs be the set of first names? In the second example, what would the domain be if my ordered pairs are first folks' heights, then their weights?
Height.
Domain would be the heights, beautiful. And the range would be the
Weight.
weights. And now with this third example, I'm going to write it a little bit differently. D stands for domain. If I put that subscripted S, that means the domain of S. And so here, when I have these specific ordered pairs, what would you tell me are in the domain? What are the first members from the pairs?
1, 2, 3, -1, -2.
1, 2, 3, -1, -2, and you're beautiful. Thank you, spot on. In the same way, if I have R sub S, that would be the range of S. And if I ask for the second numbers, what would you tell me they are?
1, 4, 3, 9, 1, 4.
I think the 3 is the first member, so 1, 4, 9. But then there's this other thing that when you list a set, you only list each element once. And so with this one, I'm going to just say that the range is 1, 4, and 9. I totally understand why you're saying 1, 4, 9, 1, 4. But because 1 and 4 are in my set already, there's no need to repeat them. I think that goes back to my theory that mathematicians are intrinsically lazy and don't like to write. And if that's all right with respect to parts of relation, what we're going to do now is we're going to go and we're going to look at what makes a relation a function. And a function, at its most basic, is a relation. And so that's telling me that a function is a set of ordered pairs. A function has a domain. A function has a range. What makes a relation a function, though, is it's a relation in which each member of the domain is paired with one and only one member of the range. Each member of the domain is paired with one and only one member of the range. For practical purposes, what does that mean? That means that each x value is paired with only one y value. Each x value has a single y value pair. And so in terms of that idea, some people look at it as the fact that each x value is used only once. The x values cannot repeat. So looking at some examples, let's look at that set S before that had the pairs 1, 1, 2, 4, 3, 9, -1, 1, and -2, 4. And this time I want to know is S a function? And to make that determination, I'm going to look at each ordered pair. This ordered pair has an x value of 1. Does any other ordered pair have an x value of 1? No. This has an x value of 2. That's the only 2. This has an x value of 3. That's the only x value of 3. This has an x value of -1. That's the only x value of -1. And over here, that's the only x value of -2. So is it a function? Yes. No x value is repeated. If I look at another example, let's look at a set T. And inside T, let me put the ordered pairs 1, 3, 2, 4, 3, 5, and 4, 6. And I want to know what's the domain of T, what's the range of T, and is T a function? And so to find the domain of T, I want a list of all of the first members, like all of the x values, which would be, anybody?
1, 2, 3, and 4.
Beautiful. And when I look for the range of T, the y values would be
1, 4, 9. Oh wait, yeah. 1, 4, 9, 1, and 4.
Yep.
Oh no, oh my god, I'm reading the wrong one.
you're looking at S, so let's go down to T. Go ahead.
3, 4, 5, and 6.
3, 4, 5, and 6. I like it. And now, is that a function? Is there any x number that shows up in more than one pair? I'm thinking each x value is only used once, so yes, it is a function. Another example, let's have V be the set of ordered pairs 5, 2, 6, 2, 7, 2. And I want the domain of V, the range of V. And I want to know, is V a function? Domain would be
5, 6, and 7.
range would be
2, 2, and 2.
2, 2, and 2. So we're only putting that 2 in once. There's no need to repeat. And now, is it a function?
Yes.
Yes, it is. Beautiful. Because each x value appears once. Notice y repeats. It's okay for y to repeat. It's just not okay for x to repeat. And one more example. This time, let's have u be the set 1, 2, 2, 4, and 1, 3. And I want the domain of u, the range of u, and I want to know, is u a function? So when I look at u, the first members would be 1, 2, and 1. So we'll just write the set 1, 2. The range, the second members would be 2, 4, 3. But now, is this one a function?
No.
No.
No. Does everybody see that 1 is paired twice? And so that's what makes it not a function. So far, so good?
Yep.
Great. Then beyond that, sometimes a function, or in general a relation, is given by an equation. If it's given by an equation, x is called the independent variable, and y is called the dependent variable. And that's because usually when we look at an equation, we pick an x value, put it in, and find the y value. So x can be any number, it's independent. And what we get for y depends on what we put in for x. And so we could have, for an example, something like x plus y equals 7. And so again, x is dependent, y is independent. And to determine if it's a function, what we want to do is we want to solve for y in terms of x. And so if I take that equation, x plus y equals 7, to solve for y to get the y alone, we'd subtract x from both sides, and we get y equals 7 minus x. And now I want to know is, if I substitute a value for x, do I only get one y value? When I put in an x number, looking at this equation, 7 minus x, for each individual x value, wouldn't I only get a single y value? And so here the answer would be yes. So we say it is a function. Another example. Let's say I have x squared plus y equals 25. And I want to know if it's a function. And so to decide if it's a function or not, I'm going to solve for y. And that would give me subtracting x squared from both sides. y equals 25 minus x squared. And again, no matter what number I put in for x, wouldn't I only get one answer, y? And so this is a function. So what would it have to look like if it's not a function? Let's say I have instead x squared plus y squared equals 49. Here, if I were to solve for y, I get y squared equals 49 minus x squared. And then if I think of using that square root property to solve for y, when I take the square root of both sides, does everybody remember over here we put a plus and minus sign in front of the radical? Because we're not sure if we're referring to the positive or the negative root, we want to consider each. And so that gives me y equals plus or minus the square root of 49 minus x squared. And you see over here, I get two y values for each x value, one from the positive and one from the negative. I guess the only exception would be if x were 0, then we'd only get one. But for the most part, we'd get two y values for every x value, and so it's not a function. So far, so good? If so, next place we're going to go is we're going to discuss the graph of a function. And the graph of a function is the set of points whose coordinates, whose ordered pairs are in the function. And so I'm going to recycle some of what we did. If I look at B, which was the set 5, 2, 6, 2, and 7, 2, if I wanted to look at its graph, I'm going to draw a set of axes, label my x, label my y, put a scale on them, and I'm going to look at the points 5, 2, 6, 2, 7, 2. And looking at those points, is it obvious that for each distinct x value, I'm only getting one point and therefore one y value? Instead, if I look at that set U, that was 1, 2, 2, 4, and 1, 3. And if I go to plot those points on my axes, x, y, I've got the point 1, 2. I've got the point 2, 4. And then I have the point 1, 3. And looking at this graph, by inspection, Does everybody see that when my x value is 1, I have two distinct points. I have two y values. And that leads me to the idea of something that's called the vertical line test. That says a graph is that of a function if any vertical line, pardon me, intersects the graph at most one point. And so applying that to these graphs that I have of just points, does everybody see in the graph of view, this vertical line intersects it twice. So it fails the vertical line test and it's not a function. Instead, if I scooch up a little bit and look at my graph of V, you see that any vertical line will cross it at most one point. So this one is a function. Usually, in making those types of determinations, we have other types of graphs to consider. And so let's say, for example, these are my axes. X and Y. And let's say my graph is this slant line. And I'm wondering, is this slant line that of a function? So if I picture all of the vertical lines, or if I picture, if we were on campus right now and I was working at a document camera, I'd take a piece of lead out of my pencil and I would roll it along the graph. And would you notice that as it rolls along the graph, every vertical line, every place it stops, the lead would only hit one point on there. And so the answer here would be yes. Then we could look at something that's more like a curve, like this. This would be considered, we'll find out later, a parabola. And when I look at my parabola, does everybody see that every vertical line would only hit it once? And so this would pass that vertical line test. And if I were asked if it were a function, I'd say yes. Instead, oh dear, there we go. Let's say I have a parabola that instead of opening vertically, opens horizontally. And here, if I ask if this is a function, well, if I drew a vertical line over here, does everybody see that here, this vertical line? Oh Lord, the stylus is not liking me right now. Give me a minute. Vertical line would cross twice, and so it fails the test. Oh dear. Sorry, I'm having technical difficulties. Give me a minute. It fails the test, so it's not a function. And one last example. Later in the semester, we'll look at graphing circles. And if I graphed a circle, would this be a function?
No.
No. Because again, as long as I can draw at least one vertical line that intersects it more than once, we're going to fail the test. Sometimes we're asked, looking at a graph, to find the domain and range. And actually, before we do it by looking at a graph, let's find the domain and range from an equation. And there, if it's not given, if we're not told what the domain and range is, it will be, it's all real numbers for which it is defined. And so to find out where something's defined, well, with our experience so far in algebra, most things are defined. There are only two things that are undefined. And so what we have to watch for, well, what's undefined? A zero denominator. So what would that look like? Let's say, for example, I have y equals 1 over x minus 2, and I'm asked what's the domain. Well, it's a fraction. I know it's undefined if my denominator is 0, and we've done this already. We've set those denominators equal to 0, and we've solved to get the values that can't be in our solution set when we were looking at solving an equation. So my domain I can write in one of two ways. I could say it's the set of all x such that x does not equal 2, x can't equal 2. It would give me a 0 in the denominator. Or I could write it in interval notation. It can be any number except 2. So it can be any number smaller than 2 up till 2. Or, taking the union, it can be any number bigger than 2, but not including 2. I believe sometimes they ask you to put it in interval notation, and other times saying giving the inequality would suffice. Besides the 0 in the denominator, if we're restricting our thoughts to real numbers, the other thing that we have to watch out for is radicals. If we're only looking at real numbers, that tells me that the radicand cannot be negative, so it must be non-negative. So what would that look like? Let's say I have y equals the square root of 2x plus 4. If the radicand is non-negative, that means what's underneath the radical, 2x plus 4. If it can't be negative, it has to be greater than or equal to 0. That's the way we would write symbolically non-negative. Well, that gives us an inequality to solve. I would get 2x is greater than or equal to negative 4, and dividing x is greater than or equal to negative 2. So for the domain, set builder notation, I'd say it's the set of all x such that x is greater than or equal to -2. Or interval-wise, the smallest value is -2, and I'm using the closed interval because it can equal -2, and there's no greater value, so I'll go the interval from -2 to infinity. And again, remember, if I'm one of my quote-unquote limits is infinity, that's always going to be that soft parentheses because we don't equal infinity. We're also asked to sometimes find the domain and range from a graph. And here I want to apologize. I can't draw that well, and so I'm going to pull up a page from the virtual textbook and use their diagrams. I'm not going to answer the question asked, but rather I'm just going to look at these for now and try to find the domain and range from a graph. So in the virtual textbook, right now, oh crap. It logged me out, and so I'm going to have to go through and reopen it. And it's not going to let me get back into Blackboard. I'm sorry, MyLabs for a minute. So I'm going to have to go back into Blackboard. I'm sorry. And so as I open the course home, I'm going to, I apologize. I should have taken a picture of this page. Go to my multimedia library. In my multimedia library, we are in chapter, oh, no, I'm not. I'm not in chapter 1, I'm in chapter 2. And I'm going to go to section 2.2. I want my textbook. And so I'm going to open the book. And actually, I don't want 2.2, but rather I want the problems at the end of 2.1. And it's usually less page flipping. And I'll go to 2.2 first. So I had this open at the beginning of class, and what happened was that we timed out. Oh dear. It's freezing in here. I think it was on page 233. Yeah, one more, 232. So I'm going to look at all these graphs, and for some of them, I'd like to go through and figure out what the domain and range are. If I first look at this one, number, oops, wrong button. '87. When I look for the domain, I'm looking at the x values. So I want to compare this graph to my x-axis. when I compare it to my x-axis, my horizontal axis, I'm wondering how far does it go to the left? Does it have a stopping point on the left or does it keep on going?
Keeps on going.
So it goes from negative infinity to, does it have a stopping point on the right? Keeps on going.
No, positive infinity would it be?
Yep. Now, instead of I ask for the range, when I look at this graph and I compare it to my y-axis, along the y-axis, does it have a lowest point or does it keep on going? I think it keeps on going down. So that's negative infinity. But does it have a highest point? Does it top out somewhere?
No. Oh wait.
Yeah,
Oh, yeah.
doesn't it stop at -2?
Yeah.
And it does equal -2. Instead, if I look at 89, when I look at 89, what would you tell me the domain is?
Negative infinity to positive infinity.
Beautiful. Instead, if I asked what the range is,
Would it be -1 with the soft parentheses to infinity?
I like the idea that it goes to infinity, but let's read this fine print here. It says it approaches but never touches the x-axis. And so the x-axis would be where y is 0. So I'm thinking it's soft parentheses 0 to infinity. Okay? And
Find the range. I'm sorry.
say that again? Go ahead.
How do we find the range of an equation?
At this stage of the game, to find the range of the equation would be kind of beyond the scope of the course. You could get it by looking at the graph. In order to find the range of an equation, you'll learn when you get to pre-calculus and calculus, what you do is you solve the equation for x in terms of y and see where that's defined.
Okay.
Okay. But again, that's something that in my teaching career at NTRIP hasn't really been touched until calculus. So I wouldn't stress too much about that one, all right?
Okay.
And so if those are all right, finding the domain and range from a graph, what we want to do next is we want to look at function notation. When I look at function notation, what I realize is that sometimes a function is given a name. So what the heck? Let's say, for example, I have something like y equals 4x plus 5. Well, I might be told that f is the function y equals 4x plus 5. With function notation, we could write that as f parentheses x, and that we read as f of x, and f of x just means y. And so f of x is actually the y value. So what we had written up here, instead of saying f is the function y equals 4x plus 5, we'd write f of x equals 4x plus 5. And again, that f of x is just another way of writing 5. And so one of the reasons that we do this is for ease in evaluation. So let's say, for example, I know that if y equals 4x plus 5, you might be asked to find y when x is equal to 1. If I were asked to find y when x is equal to 1, well, I'd say that y is equal to 4x plus 5. And what would you do with that 1? Wouldn't you put it in for x?
Yeah.
And that would give me y is equal to 4 times 1 plus 5, which could give me y equals 9. And so we could say that when x is 1, y is 9. Or we could write that as a 0.19. Well, with function notation, I could just write that as if f of x equals 4x plus 5, I might ask you to find f of 1. And over here, when I write f of 1, do you see what I did was I replaced x with 1. And so over here in the name of the function, if I replace x with 1, that tells me everywhere else where there is an x, I want to put a 1. And so when I work that out, I still get my 9. So I would say f of 1 is equal to 9, which would be telling me when x is 1, y is 9. And in general, if f of x is my function or relation, to find f of a, we substitute a for x. So that's the beauty of function notation. Let's say, for example, I'm given that g of x equals 3x minus 6, and I want to find, let's find g of negative 4. Let's find g of 5. Let's find g of 7. Let's find g oh dear. I just replaced the battery in this thing. I don't know why it's not liking me. Let's find g of negative x, and let's find g of x plus 2. Well, again, where I have g of x equals 3x minus 6, I can think of that x as a placeholder. And whatever goes in for x in the first parentheses is going to go in for x in the rest of the equation. So g of negative 4 would be 3 times what I'm putting in for x minus 6. And I'm putting in negative 4. So 3 times negative 4 would be negative 12 minus 6 would be negative 18. G of 5 would be 3 times whatever I'm putting in for x minus 5. And this time I'm putting in 5. I'm sorry, whatever I put in for x minus 6. I apologize, I misspoke. And so when I work this out, I have 15 minus 6 or 9. G of 7, well, it would be 3 times, I'm replacing x with 7 minus 6. And 21 minus 6 would be 15. And that's the same if I substitute in a variable. G of negative x, where I had an x, I'll put negative x. That'll be negative x minus 6. And now here, if I simplify, 3 times negative x would be negative 3x minus 6. And I can put in something more than a single value. I can put in something like a binomial. G of x plus 2, that's 3 times, I'm replacing x with x plus 2 minus 6. And again, it keeps you from making careless mistakes if you put parentheses around what you substitute. Because here, putting parentheses around what I substitute, does everybody see the need to distribute? So that would give me 3x plus 6 minus 6. And so my final answer here would be 3x. So I'm going to shut up for a minute and ask you folks to try some. This time, let's say f of x is equal to x squared plus 2x plus 3. And I want f of negative 1. I want f of 3. And I want f of x plus 2. And I'm going to be real quiet for a minute and have you folks do that. How are you folks doing? Are you done yet, or do you need a little bit more time?
You're good.
You're good? So f of 1, did everybody get 2? I'm
Yes.
sorry, f of negative 1. If I take negative 1 squared plus 2 times negative 1 plus 3, I get 2. When I substitute in 3, I get 3 squared plus 2 times 3 plus 3. That'll give me 18. And the one I'm more concerned about is this last one. This last one, I would have to take the quantity x plus 2 and square it, add to that 2 times x plus 2, and then add to that 3. And did everybody working that one out get x squared plus 6x plus 11? Everybody okay? Not hearing any concerns. Then I'd like to go back and look at those graphs from the book again and look at the idea of finding function values from a graph. And again, in the virtual textbook, I think we're on page, what was it, 232 by the time I finished scrolling around. And so as I look at, let's say, number 87, question number 87, first asked us to find f of -4. And again, this -4 is in the place for x. So I'm saying when x is -4, if I go down to my graph, what would you tell me y is? When x is -4, the point on the graph, what would it have a y value of? I don't know, does that look like 5 to anybody else? And with that one also, what if I asked for f of 4? On that graph, when x is 4, what would you tell me the y value is? Looking at it, whoops, that wasn't 5, that was -5. I apologize. And for the next one, it would be -2. Let me look over here at number 90. Number 90 asks me for f of 2. And so here I'm looking for when x is 2 on my graph, what would you tell me the corresponding y value is? I'm going through this point here. When x is 2, isn't the y value 1? Is that all right? Is everybody okay with reading coordinates off a graph?
Yep.
And what you have to remember with function notation is that number that's in the parentheses next to the letter of the function is the x value. If that's all right, the next section spends a little bit more time looking at the idea of the graph of a function.
Is this 2.2?
I think this is kind of on the border between 2.1 and 2.2. I think a little bit might show up in 2.1, but it is probably more 2.2. And it's one quality of a graph that we look at is the intercepts. And the intercepts are the points where the graph crosses the axes. We're going to find that we sometimes talk about two different types of intercepts. If I look for the x-intercept, it's the point where the graph intersects the x-axis. And so I'm going to draw a set of axes. And the x-intercept, by its nature, has to be a point on the x-axis. And if I look at all of the points on the x-axis, what they all have in common is they have a y value of 0. So to find it, what we're going to do is we're going to substitute y equals 0 and solve for x. And we'll get a point with a y value of 0. Instead, if I want the y-intercept would be the point on the y-axis. And again, if I look at all of my points on the y-axis, I'm doing my beautiful point drawing over here on the side, what they all have in common is an x value of 0. So to find from an equation, we'll substitute x equals 0 and solve for y. And we'll get a point with an x value of 0, and the y value will be the intercept. So if I look at an example, I might be asked to find the intercepts of, let's say I have an equation 3x plus 4y equals 12. Well, to find the x-intercepts, I'm going to plug in 0 for y. Gives me 3x plus 4 times y is 0 equals 12. Gives me 3x equals 12. And so dividing, I'd get x equals 4. So my x-intercept would be the point 4, 0. Similarly, if I'm asked to find the y-intercept, to find a point on the y-axis, I'll let x equal 0. And so my equation 3x would be 3 times 0 plus 4y equals 12. Well, 3 times 0 is 0, plus 4y would just be 4y equals 12. And dividing by 4, I'd get y equals 3. And so my y-intercept would have an x value of 0 and a y value of 3. Make sense?
Does.
Okay, good. If that's all right, then this is where I end it with the other section. I know we have 3 minutes of class time left, but are you folks all right if I call it a day? Will you fault me for not giving you 3 minutes worth of your tuition? So I know
Okay.
you'll be okay. Okay, make sure you get through that test before the end of the day on Saturday. A couple of you came in late. Let me make sure I get you on attendance. Ryan, I've got you. Who else came in afterwards? Anybody else that's here come in
I
after?
did.
Whose I did?
Olivia.
Olivia? Olivia, I got you. You got in just as we were finishing attendance, and so I did get you. Thank you for making
Okay,
sure.
thank you.
Okay, have a good weekend.
You
Anybody
too.
else? All right, anybody have any questions? Anybody sticking around for questions, or are you just... Mikhail, you all right? Have a good weekend.